Let's talk about Mars for a minute. It's the closest planet to us that you could actually stand on. It's got a day that's almost identical to ours, about 24 hours. It has polar ice caps that grow and shrink with the seasons. It has canyons that would swallow our Grand Canyon without a trace, and a volcano so massive it dwarfs anything on Earth. When you listen to the true believers, the ones with the gleaming presentations and the ambitious timelines, you get this very clear picture. The only things standing between us and a cute little Martian colony, they'll tell you, are a slightly better rocket engine and some clever architectural plans. You build a habitat, you ship up some food, you pressurize a dome. Simple. Key in the code and move in. And on the surface, that sounds completely reasonable. It sounds like an engineering challenge, a big one, sure, but fundamentally the same kind of problem as building a submarine base or a space station or a research outpost in Antarctica. It's hard, it's expensive, but it's solvable. After all, we put people on the moon, right? So Mars must just be a longer road trip. You just need a bigger lunchbox. That idea? It is catastrophically, fundamentally wrong. And the beautiful, brutal thing is, I don't need a complex NASA study to prove it to you. I can show you why with nothing more than some basic high school physics. The core problem with Mars isn't the distance. It isn't the travel time, though that's certainly a factor. The problem is that Mars is actively, aggressively, and simultaneously trying to kill you in about half a dozen different ways. And the really nasty part is that most of these ways aren't engineering challenges. They are physics problems. And physics problems have a way of not caring about your budget, your timeline, or your optimism. They just sit there, immovable and true, regardless of what you want. So let's take a walk through what Mars actually is, physically, and why those beautiful artists' renderings of little greenhouses on a red plain are leaving out a few crucial, life-ending details. We have to start with the most basic thing: air. You need it. On this planet, right now, you are at the bottom of an ocean of air. It's a thick, heavy blanket pressing down on you with a force of about 101,000 pascals. We call that one atmosphere. Your body is exquisitely calibrated for it. Your lungs, your blood vessels, the fluid balance in every single one of your cells, all of it expects that pressure. Now, Mars has an atmosphere. People love to point that out. Great. Except the average pressure on the surface of Mars is about 600 pascals. Let that sink in. 600. That's less than 1% of the pressure you're breathing right now. To experience that pressure on Earth, you'd have to go up to about 45 kilometers. That's not a mountaintop. That's 3 times higher than a commercial jet flies. That's the edge of space, where the Air Force starts worrying about their pilots in pressure suits. And it gets so much worse. There's a concept in aerospace medicine called the Armstrong limit. It's named after an Air Force surgeon who figured this out in the 40s. The Armstrong limit is the altitude where the atmospheric pressure drops so low that water boils at the normal temperature of the human body, which is 37 degrees Celsius. On Earth, that altitude is about 19 kilometers up. Above that point, any exposed fluid on your body, your saliva, the moisture on your eyeballs, the thin film of liquid lining your lungs will begin to boil, not because it's hot, but because the pressure is too low to keep it liquid. The pressure at the Armstrong limit is about 6,300 pascals. The pressure on Mars is 600 pascals. Do you see the problem? Mars isn't just below the Armstrong limit, it's 10 times below it. If you stepped onto the surface of Mars without a pressurized suit, the moisture on your tongue would instantly vaporize. Your eyes would swell. The fluids in your lungs would flash to gas. You wouldn't suffocate quietly. Something far more violent would happen first. It's called ebulism. Gas bubbles would form in your tissues. Your body would swell grotesquely. You'd be unconscious in about 15 seconds and dead in a couple of minutes. But let's say, for the sake of argument, you could magically pressurize that air enough to breathe. You'd still be in profound trouble because of what that air is made of. The Martian atmosphere is 95% carbon dioxide. There's a smidge of nitrogen and argon, and a whisper of oxygen, about 0.3%. That's essentially zero. On Earth, the air you're breathing is about 21% oxygen. Your body needs a partial pressure of oxygen, a certain concentration of it in the mix to function. On Mars, even if you raise the total pressure to Earth levels, the partial pressure of oxygen would still be far too low to sustain you. And the carbon dioxide, At those concentrations, it's not just inert, it's actively poisonous. Breathe air that's 5% CO2 and you get headaches and confusion. At 10%, you lose consciousness. At 95%, it would kill you faster than the lack of oxygen would. So the air attacks you from 3 directions at once. The pressure is too low, the oxygen is too scarce, and the main component is a toxin. And we haven't even touched on the ultraviolet light. With no ozone layer because there's almost no free oxygen to create it, the surface is bathed in unfiltered, sterilizing UV radiation. It's like living under a giant germicidal lamp. You could put a petri dish of bacteria in the Martian sun, and they'd be dead in minutes. So no, you can't step outside for a breath of fresh air. That much is obvious. But here's what's less obvious. On Earth, a crack in a wall, a leaky window, a bad seal on a door, these are annoyances. On Mars, any breach in your habitat is not a leak. It's a detonation. The pressure difference between the inside of your home and the outside world is nearly a full atmosphere. Your entire living space is a pressure vessel. Every wall, every window, every airlock is holding back an explosive force. Your home is a balloon, inflated to nearly 15 pounds per square inch, sitting in a vacuum. Now think about that in terms of reliability. Every single weld, every seal, every joint, every hatch has to hold that pressure difference. Not for a week, not for a month, for years, for decades. A colony implies permanence. And any failure, anywhere, is an extinction-level event for the people inside. On a submarine, if you get a leak, water comes in. You have time to react. On Mars, if you get a leak, air goes out. It screams out of any opening because the pressure gradient is so immense. You might have seconds. This is not an unsolvable problem in isolation. We build pressure vessels, but it fundamentally changes the nature of what you're building. You're not building a house. You're building a spacecraft that never moves. And every spacecraft we've ever built requires constant, obsessive maintenance and has a limited operational life. The ISS has crews that rotate, equipment that gets replaced, modules that eventually get retired. No one lives there permanently. Then there's the issue of fatigue. Materials under constant stress degrade. Metals crack. Seals harden and lose their elasticity. On Earth, a building can stand for centuries because the loads are modest. On Mars, your walls are under constant tension. Every thermal cycle, and Mars has temperature swings of 100 degrees Celsius between day and night, makes your structure expand and contract, day after day, year after year. This stresses every joint, every seal. On Earth, thermal cycling is a known cause of failure in bridges and aircraft. We manage it with constant inspections and part replacements. On Mars, who inspects? Who replaces, and with what spare parts, made from what manufacturing base? And don't forget the dust. Mars has global dust storms that can shroud the entire planet for months. This dust is fine, abrasive, and gets into everything. It will coat your solar panels, clog your filters, and over the years, it will sandblast every exterior surface, grinding away at those critical seals. All right, let's move to the second problem. This one is sneakier. It's radiation. On Earth, we're protected by 2 things. First, our magnetic field, generated by the churning molten core deep within our planet, deflects most of the high-energy charged particles coming from the sun and the rest of the galaxy. Second, the thick atmosphere acts as a physical barrier. Any particles that get past the magnetic field still have to plow through miles of air, which absorbs and scatters them. Mars has neither of these things. Its core cooled billions of years ago. The magnetic dynamo shut off. With that shield gone, the solar wind was able to directly strip away its atmosphere, molecule by molecule, over eons. The rivers and lakes vanished. The planet died because its heart went cold. Recent simulations even suggest that a weak, dying magnetic field, like the one Mars had for a while, might have actually accelerated the process, funneling atmospheric particles out into space even faster. So today, Mars is a sitting duck. The thin, wispy atmosphere of CO2 stops maybe 1 or 2% of incoming cosmic radiation. Compared to Earth's atmosphere, which is like a wall of lead, Mars' atmosphere is like holding up a single sheet of tissue paper against a fire hose. So what hits the surface? 2 main things. First, galactic cosmic rays. These aren't from our sun. They're from across the galaxy. Supernova remnants, violent cosmic events. They're mostly protons, but about 1% are heavy ions, like iron atoms, stripped of their electrons and accelerated to nearly the speed of light. When one of these heavy ions hits living tissue, it doesn't just cause a little bit of damage. It plows a track of destruction through your cells like a microscopic cannonball, shattering DNA strands and causing complex damage that your body's repair mechanisms can't fix. The second threat is solar particle events. The sun periodically belches out enormous clouds of high-energy protons. A big event can deliver a huge radiation dose in just a few hours. On Earth, our magnetic field deflects them. On Mars, you just get hit. Instruments on the Curiosity rover have measured the radiation. An astronaut on Mars would accumulate about 2/3 of a millisievert per day. Over a year, that's about 240 millisieverts. The average person on Earth gets about 6 millisieverts per year from natural background radiation. So you're soaking up 40 times the natural dose every single year. And here's the really insidious part. Galactic cosmic rays are incredibly difficult to shield against. For solar events, you can hide behind something dense. A few meters of Martian soil would work great, but when those high-energy, heavy nuclei hit shielding material, they don't just stop. They shatter. They undergo nuclear fragmentation, producing showers of secondary particles, neutrons, gamma rays, that can be even more damaging than the original particle. NASA has run the numbers on aluminum shielding, the kind we usually use in space. Beyond a certain thickness, adding more aluminum actually makes the radiation dose worse because you're creating more secondaries than you're stopping primaries. The only materials that help are hydrogen-rich ones, like water or plastic. But you need a lot of it, several meters of it. To protect an entire habitat, that's an almost unimaginable amount of mass to haul from Earth or dig up and process on site. This isn't a manageable problem. It's an open research problem. NASA's own experts have said that with current technology, a Mars mission would exceed acceptable career dose limits for astronauts. Studies on animals exposed to simulated galactic cosmic rays have shown persistent cognitive impairment, memory problems, difficulty with decision-making, reduced ability to extinguish fear responses. The damage was measurable months after exposure. The radiation physically reduced the complexity of neurons in the prefrontal cortex, the part of your brain you use for planning and judgment. The very environment you're living in would be slowly degrading the one organ you absolutely need to make life or death decisions 8 months from the nearest help. That is not an engineering problem. That is physics and biology fighting, and currently, biology is losing. And I haven't even mentioned the dirt. The soil of Mars is toxic. This is a detail that always gets glossed over because soil just sounds so benign. It's dirt, right? But Martian regolith is laced with perchlorate compounds. The Viking landers discovered this in the 70s, and Phoenix confirmed it. Perchlorates are highly reactive oxidizing agents. On Earth, perchlorate contamination in water is regulated at the parts per billion level. In Martian soil, it's measured in parts per million. If you ingest it, it messes with your thyroid gland, disrupting hormone production. Chronic exposure leads to hypothyroidism. In children, it impairs cognitive development. And on Mars, this stuff is in the dust. And Martian dust is incredibly fine, finer than talcum powder. It gets into everything. It will infiltrate your habitat, your equipment, your lungs. Inhaling these fine, sharp particles could cause inflammation and fibrosis, the same kind of irreversible lung damage you get from asbestos or silica. So the very ground you're standing on is poisoned, and the dust from that ground is constantly trying to get inside you and break your gear. Any attempt to grow food would require either extensive soil processing to remove the perchlorates or a complete hydroponic system, which brings us right back to the problem of energy. Let's shift gears and talk about something that sounds hopeful. Gravity. Mars has about 38% of Earth's gravity. You can walk. Things fall. It feels like something. But here's the multi-billion-dollar question that nobody can answer. Is 38% enough? We know what zero gravity does. Astronauts on the ISS lose bone density at 1 to 2% per month. Their muscles atrophy. Their cardiovascular systems decondition. They exercise for 2 hours a day just to slow the decay, and they still come back to Earth profoundly weakened. After 6 months, some need to be carried out of the capsule. Some bone loss may never fully reverse. That's in 0G. On Mars, you have 38%. That's better than zero. But is it enough to maintain human health for years? A lifetime? We have zero data. We've never studied long-term partial gravity. The longest anyone has spent on the moon is about 3 days. That tells us nothing. Indirect evidence is not encouraging. Some reviews suggest that gravity below about 40% is probably insufficient to maintain muscle and bone health over the long term, even with exercise. Think about what that means for a colony. You're going to raise children on Mars, children whose bones, muscles, and organs develop in 38% gravity, children who may never be able to come to Earth because their bodies couldn't handle the load. Nobody has studied fetal development or childhood growth in partial gravity. This is not pessimism. It's an honest admission of how much we simply do not know. Now let's talk about the one thing that underpins everything else, energy. Everything on Mars requires a staggering amount of energy. Heating your habitat is a constant draw because the average surface temperature is 63 degrees Celsius. In winter, at the poles, it gets cold enough that carbon dioxide freezes out of the atmosphere and falls as snow. You must heat your habitat continuously or die. Producing breathable air requires energy. You need to crack CO2 molecules or electrolyze water to get oxygen. Producing water requires energy. There's ice under the surface, but you have to mine it, haul it, melt it, and purify it. Growing food requires energy. Mars gets about 43% of the sunlight we get, so any greenhouse needs supplemental lighting. And all of this equipment needs maintenance. It needs replacement parts. Manufacturing those parts, even with 3D printers, requires energy. Smelting metal from ore requires energy. Where does it all come from? Solar panels work, but they produce less than half the power they do on Earth. And those global dust storms I mentioned, they can blot out the sun for weeks or months. Remember the Opportunity rover? It died in a planet-wide dust storm because its panels couldn't get enough light. Nuclear power is the obvious alternative. Small fission reactors could provide steady, reliable power, but they require heavy shielding, expert maintenance, and a supply of fuel. You either bring it all from Earth or you figure out how to mine and refine uranium on Mars, which requires an entire industrial infrastructure that doesn't exist. And there's a human element to this energy problem. On Earth, if your power plant breaks, you call a repair crew. On Mars, your repair crew is the same 6 people who are also the doctors, the geologists, the farmers, the plumbers, and the cooks. Every person is a critical component of the system. If one gets sick, the whole operation is degraded. There are no specialists on call. There's no workforce to draw from. And they're doing all of this in an environment that is physically exhausting, psychologically isolating, and potentially brain damaging from radiation. Which brings us, finally, to the human mind. Cosmonauts on the Mir space station who could look out the window and see Earth, who could talk to their families in near real time, who knew they could come home in an emergency, still reported significant psychological effects. Depression, irritability, sleep disruption, explosive interpersonal conflicts in a tiny confined space. On Mars, you are so far away that home becomes an abstraction. The time delay for communication is between 6 and 44 minutes one way. You can't have a real conversation. You can't get real-time counseling. The psychological pressure of knowing you are utterly, fundamentally alone, with no possibility of a quick rescue, with no escape if things go wrong, is something no human has ever endured for more than a few days. And those were the Apollo astronauts, who were only 3 days from home. A Mars crew would be isolated for a minimum of 2.5 to 3 years. Some proposals talk about one-way trips, people who go and never come back. Think about the psychology of that small community. A dozen people trapped together in a space the size of a few apartments, knowing that this is it. This is the rest of their lives. Human beings evolved in groups of a few hundred, with open landscapes and the ability to walk away from conflict. On Mars, you cannot walk away. You cannot take a break. You cannot visit another town. The walls of your habitat are the borders of your entire world. And unlike in Antarctica, where the air is breathable and you can step outside, here the outside is a lethal, radiating, poisoned vacuum that is constantly trying to break in. The energy budget for keeping a human alive on Mars is not just about watts and joules. It's about the human spirit's ability to endure a reality for which it was never designed. And that's a problem physics can't solve. Here is an additional segment designed to be woven into the script, adding roughly another minute of spoken content. It focuses on the psychological and societal challenges in a more visceral way, building on the ending. And that's a problem physics can't solve. But let's push on that last thought for a moment, because it's where the diagrams and the mission patches really start to lie to us. They show us the hardware, the HABs, the rovers. They don't show us the interior life of a person who knows with absolute certainty that they will never again feel rain on their face, never again walk through a forest, never taste food that wasn't grown in a hydroponic tray under artificial light, never have a conversation that doesn't have a half-hour pause built into it. We talk about colonizing Mars as if we're talking about the pilgrims sailing to a new world. But the pilgrims could breathe the air. They could drink the water. When the ship sailed away, they knew that another ship could eventually come back. The fundamental backdrop of their existence was a living, breathing planet. The fundamental backdrop of a Martian colonist's existence is a dead world that is, at every second, trying to kill them. Think about the constant low-grade hum of dread that would permeate every moment. You are living inside a machine. Your home is a life support system. And you know intellectually that any one of 1,000 things could go wrong. A seal fails, a pump seizes, a meteoroid, even a tiny one, punches a hole in the wrong place. The margin between life and death isn't a cliff you might fall off. It's a thin, brittle sheet of ice you're skating on every single day. That awareness doesn't go away. It becomes the wallpaper of your mind. And what happens to society when it's built on that kind of foundational anxiety? When every single person in your community is not just a neighbor, but a critical, non-replaceable component of the system that keeps you alive? If someone makes a mistake, it's not just an inconvenience. If someone has a mental breakdown, it's not just a personal tragedy. It's a direct threat to everyone. How do you manage conflict in a pressure cooker where you can't take a time out? You can't go for a drive to cool off. You can't even go for a walk outside. The person you're furious with is the same person you'll be sitting 3 feet away from at dinner, and the same person who might need to perform emergency surgery on you next week. We haven't even scratched the surface of how a society like that would govern itself. What are the rules? Who enforces them? What happens if someone commits a crime? You can't build a prison. You can't banish them outside the airlock. That's just murder with a different name. Do you live in a constant state of enforced politeness where every grievance is suppressed because the cost of expressing it is too high? That pressure has to go somewhere. It builds. It festers. We talk about Mars as the next frontier for human ambition. But frontiers in human history have always had an exit. You could always pack up your wagon and head back east or push further west. On Mars, there is no exit. There is only the HAB. There is only the same 6 faces, the same recycled air, the same hum of machinery for years. The data from simulations here on Earth, like the HIC's experiments in Hawaii, are telling. Crews isolated for months in simulated Mars conditions report the same patterns. Interpersonal tensions, factions forming, the psychological toll of monotony and confinement. And those simulations are on Earth. They can step outside anytime they want. They're not actually facing death. So when you add it all up, the physics, the biology, the psychology, the image of a bustling colony on Mars starts to look less like a human future and more like a human prison. A prison made of titanium and regolith bricks, sitting in a radiation-soaked frozen desert, where the guards are the immutable laws of nature and the sentence is for life. And the really haunting question becomes not, can we do it, but should we? What kind of person says yes to that? And what kind of society are we creating when we send them? Some proposals talk about one-way trips, people who go and never come back. Think about the psychology of that small community. A dozen people trapped together in a space the size of a few apartments, knowing that this is it. This is the rest of their lives. Human beings evolved in groups of a few hundred, with open landscapes and the ability to walk away from conflict. On Mars, you cannot walk away. You cannot take a break. You cannot visit another town. The walls of your habitat are the borders of your entire world. And unlike in Antarctica, where the air is breathable and you can step outside, here the outside is a lethal, radiating, poisoned vacuum that is constantly trying to break in. The energy budget for keeping a human alive on Mars is not just about watts and joules. It's about the human spirit's ability to endure a reality for which it was never designed. And that's a problem physics can't solve.